everyone, how are you? In this video, I will work with the time series data of Bitcoin asset prices taken from this recent Kaggle competition and apply some of the most typical feature engineering to make it ready for any tabular machine learning algorithm. And then I will apply XGBoost to come up with a prediction of Bitcoin prices. First, a little overview of the data here. So if you just go to the data tab of this competition, you will see quite a few CSV file. And for our case here, the one that we'll be using is this one, train.csv. And it's quite a large file. It's 2.82 GB. And if you just click on it, this is the whole CSV file. We have the typical column names are just typical, very common for any asset price like stock price or cryptocurrency prices data. So we have OHLC data, that is open, high, low, close. So this is open, high, low, close. This is the corresponding prices in a day or for the particular timestamp. In this case, the timestamp is actually each minute. So it's minute by minute data. And the timestamp is this right here. All these individual numbers represent a single minute and the corresponding prices of Bitcoin. And all right, and also we have volume data. This is another important feature. Then VWAP, volume weighted average price, and target. And of course, you can just read about each columns, what they represent right here in the competition page. So the target is actually 15-minute residualized returns, and the VWAP is volume weighted average price for the minute. And we also have few other CSV file here, but those will not be needed for this particular exercise. And all right, so you can just directly work with this data right inside Kaggle kernel. In that case, you do not need to download this large file. And also, if you do not have that much of computing power locally, it may be useful just to remain within the Kaggle kernel. But in my case, I have downloaded this data in my local machine and we will work there. And here I am in my VS Code and only reading the train.csv file from my local machine. And you can, if you are working directly in Kaggle, you just need to change this root deed in this variable. And in Kaggle, it would be this. All right, and because it's a large file, just reading all the rows took around 12 seconds in my local machine. And then check the shape. We have around 24.2 million lines of rows. That is, these are all individual timestamps on which we have the corresponding BTC price. And the whole data frame looks like this. I'm just printing the top two heads, top two rows. And the first column of this data frame is timestamp. And then we have asset ID, which is just represent different cryptocurrency assets. In our case, we know that the asset ID 1 actually represent BTC for this particular data set. And how do I know that? Because in the original Kaggle's official page, a separate CSV file was given in which we have a list of asset ID and the corresponding cryptocurrency. From there, we know that asset ID 1 is for BTC. All right, and then the next thing I want to do is, because it is such a large data frame, I want to optimize the memory footprint of reading and working with this data frame, because you already saw when just doing a pd.read CSV, it took 12 seconds to go through entire 24 million lines of rows. So for that, I have a little util method that has been defined in my preprocess.py, this Python file. But first, I need to check the actual memory usage for the data frame. And that also I'm doing it with another util method called getDataFrameMemoryUsage, which has been defined in preprocess.py. And this is a method. It only returns the total memory consumption of a pandas data frame in megabytes. And the main line is here, df.memoryUsage, and I'm passing deep equal to true. So this is an inbuilt method of pandas. And only point to note is that deep equal to true because I want to capture the entire memory consumed by the data frame. So when you use deep equal to true parameter, that actually include the memory usage of any objects that are referenced by the data frame's columns, such as strings or other nested data structures. If you set deep equal to false, the method will return only the memory usage of the column itself, which may not be the total memory consumed by the data frame, which I do not want in this case. I want to capture the entire memory consumed by the data frame. So that's the reason I'm using dip equal to true and then sum the memory usage to get the total memory consumed, and then dividing by this number to convert these whole numbers to its megabyte format. And with the execution of that function, get data frame memory usage, I get 1.8 GB is the total memory usage by the full data frame, which is actually huge. And so I need to reduce this overall memory usage. And for that, I have another little util method called reduce memory usage right here, defined in the preprocess Python file. And okay, so let's go through this method very quickly. But this method as well uses another small method, which is get optimal numeric type. So this will just give you this will just determine the optimal numeric data type for a given range of values. And it takes a couple of parameters. The first one is a minimum number, then a maximum number, and then the column type. And the key important lines are here in this method. So if it will check that if the mean value is greater than this particular number, and this number I'm getting from my D type of the column that I'm checking, and I'm getting the type info, this variable, with this line right here. That is, this is just equal to np.info if call type is integer, otherwise it's np.finfo. So np.info and np.finfo are two utility functions provided by NumPy to obtain machine limits for integer and floating point types respectively. So np.info returns the machine limits for integer types. It takes an integer data type as input, for example np.int8 or np.int16 or np.int32, etc., and returns an object containing the minimum and maximum values that the specified data type can represent. You can access these values using the min and max attributes of the returned object. And np.finfo does the exact same job, only thing that it deals with floating point types. And that's why I'm getting with dot mean and dot max, the maximum limit, and comparing those two limits with my cmean and cmax, which is coming as an argument to the function. And thereby the whole method is returning the D type after doing this comparison. And this function will be used in my main reduce memory usage method. And so the whole reduce memory usage, the main point that I'm doing is that I have written it here clearly. Based on the data type and the range of values, the function determines the smallest possible data type that can accommodate the data without losing information. For example, if the data type is an integer and the range of values fits within the bounds of an int8 data type, the function converts the column data type to int8. So this method is iterating over each of the column through this loop right here. And also then it checks that the data type is not an object, and if that is satisfied, then it determines the cmean and cmax by doing dfcopy call.mean and again dfcopy call.max. And because why do I need that? Because we already saw these two values that will be required by this method is cmean and cmax, and that's just the minimum and the maximum values of the respective column. All right, now that we have that, all you have to do is execute or just to run these get optimal numeric type, this method, pass my cmean, cmax, and call type str. Call type str is again defined int integer if int in str call type, else float. All right, and so as soon as I execute this method, it will give me the optimal data type for that particular column. And all I have to do is convert that respective column to this optimal type, and this line is doing just that. Df copy call, and it's doing .s type, and that is casting it with this optimal type. All right, and then finally returning the df copy, which has all the columns casted to its optimal data type. And coming back to the original notebook, when I reduce memory usage and I apply this on my full data frame, and then I check the memory usage of this full data frame. I see the data frame memory now is only 716 MB. Previously, it was 1.8 GB. All right, so we reduce the memory usage quite a bit. And next, I just need to check what is the entire trading span, that is the starting timestamp and the ending timestamp for the entire input dataset. And that's the job of these two lines. So here I'm using ilock 0, then .timestamp, casting that as type to datetime 64. So here the first line, this as type datetime 64, this part of the code is converting the value in the timestamp column to datetime 64 second format, which actually represents a datetime with a time resolution of seconds. And when I run this, I get the data from 2018-01-01 until 2021-09-21. So this is the entire time span we have in our input data set. So it's of course historical data. This data is not updated after 9/21. But here the purpose of the exercise is just to see the execute a model and how that predict against its training data. It's not really doing an actual Bitcoin future prediction based on the current data. So let's go ahead. We have approximately 3 years worth of data. This informs the type of time windows we can look into. And some of the basic visualization that I want to do is just plot a very small portion of the dataset. So I'm taking the last 60 rows here in this line and creating a new data frame, BTC mini df 60 rows. And asset ID is equal to 1 because we already discussed that 1 represent BTC, but the train.csv file has many cryptocurrencies within it, each identified by a unique asset ID. And here, for the purpose of our exercise, it is asset ID equal to 1, which we are interested in. And so I'm going to use this go.candlestick method, but there's one slight issue with our current data format. And the issue here is that for go.candlestick expects the input data to be of type float 64 or float 32. But as you already did in our previous step, that we converted each column data to its most optimized form. So some of the columns were converted to float 8, which will not be supported by go.candlestick. And that's a thing, that's the reason that I'm doing these lines here. That is, I'm converting open, high, low, close, these 4 columns back to float 32, because a float 8 or float 16 would not be supported by go.candlestick. And then when you plot the data, you get this nice looking candlestick plot. But of course, candlestick plots are just a visually appealing thing. We will delve further into analyzing the trends, cycles, and seasonal patterns of the dataset. Currently, these candlestick plot are only serving as a preliminary tool to help us obtain a basic view of the data. It doesn't really have any particular interpretation at this point. Alright, with that, the next phase of this exercise, which is pre-processing the data, starts. And the first step is doing a set index on the timestamp column. And then I'm just running a .info method on the entire BTC-DF data frame to see for existence of non-null values here. And also, actually, you can do a code like this, btc-df.isNA.sum, and that will give you on a per column basis the existence of how many not a number values or isNA values are there. So you can see the target has 304 of them. That's actually very small number of columns. But how to deal with that, we'll come to that later, because probably I'm not going to use this target column as far as I have planned to. So let's ignore these column for now, and we'll check back it later. And beyond the checking for not a number values, the more important thing is that the situation when an entire row is missing from your input data. So this is the case when you don't have any information on at all for a particular minute, in this case, because here each row represents a single minute. So which means that the whole rows may be missing from our data set. That is, we already saw we have 24 million rows spanning the entire time frame. And that means that for each minute of those entire time frame, we should have a single row. But if some of the minutes are missing, that means we have a missing value, missing row problem there. And we need to check for that and adjust for that. So we should have basically one row per minute per asset. Since we extracted the data for a single asset, we expect consecutive rows to have a difference of 60 seconds between their index values. So I want to check the time lag between consecutive entries in our dataset. And for that, I have a util method check for missing timestamp, and that is defined here. And the method is very simple. This one right here, only 2 lines of code. Basically, all it does is checks 2 consecutive rows and the time differences between the 2 consecutive rows. And the most important line here is this, which will calculate the time differences between 2 consecutive rows. So what I'm doing here is these 2 things, df.index, then 1 and a slice notation. This is one slice, and another slice that I'm doing is df.index and then slice notation -1. So basically, this entire expression slices the index into 2 arrays, one starting from the second index, that is index 1 right here, and the other ending at the second to last index, and that is captured with -1 here, and subtracting these 2 arrays, resulting in a new array of time differences in the form of pandas time delta object between consecutive rows of the data frame. And then so with that, I'm getting these time dips, and then I'm applying value counts method on it, which will count the frequency of each unique time differences and returns a pandas series object with the counts as values and the unique time differences as indices. So let's execute this method right here. When I execute this, I get this result. And this result just shows that we had initially almost 24 million rows. Out of that, all these many millions, that is 19.5 million, have 60 as the time differences. Then 78 have 120 as the time differences. Which means 78 instances where 2 consecutive entries are 120 seconds apart instead of 60 seconds. And then we have 12 instances which are apart by 180 seconds and so on. Now, given these small gaps in data, the simple imputation strategy that we can apply here is that fill the missing data with the value from the most recent available minute. And this is what we will be doing next. And we are going to do that with this small method, impute missing data. That's been defined right here, impute missing data. Again, a very small method, just involving 2 lines of codes. And here I'm just sorting the given data frame first and then creating a minute by minute index of the entire data frame. So look at this range that I'm creating right here. So this df.reindex, this method takes a range of values. Here, this particular range is starting from the first timestamp in the index of BTC-df and ending the last timestamp plus 60 seconds. This is a plus here, and with a step of 60 seconds. And this creates a new index with a minute by minute frequency. And the missing values, that is any timestamp that are not present in the original index, are filled in using the method specified by the method parameter, which I'm passing it here. which is pad here. And the pad method means that it will fill any missing value with the most recent available value. Alright, and then after that I apply this impute missing data on my original data frame BTCDF, and this is a resultant data frame. And now I need to check again definitely for existence of any missing rows. So I run this method again, check for missing timestamp on this modified data frame, and this is the result. So only all of them means are separated by 60 seconds. So that means previously we got this result. Now I get all of them, that is each and every 2 rows, consecutive rows in this modified data frame are separated by 60 seconds, and that's exactly what we want. We don't want any missing minute in this data frame. Alright, let's move on. And then we don't need the index as a timestamp anymore, so let's just have it as a date time. And for that conversion, I'm going to use this little util method set datetime index. And this will just take a data frame and an index name. Here the index name is a string, which is datetime, which is my required conversion type. And all it does is using a lambda function to convert the index of a data frame to datetime 64 seconds, this type conversion. So in this line, as you can see, what I'm doing is df.apply, then using lambda, and r in p.float64 r.name, and then casting as type to datetime 64. So this r.name here, the particular thing here, refers to the index of the row r being processed, and np.float64 converts the index values to float64 data type. And this is because when working with time series data or data that involves calculations with decimal points, it may be necessary to use a float data type for the index to ensure precision in the calculation. In such cases, float64 data type is kind of the most appropriate and preferred for its high precision and wider range of representable values compared to other floating point data types. And that's the reason I'm converting this to float64. And then as type method right here, this method is called on the float64 value with the argument datetime64s, which converts a float64 value to a datetime object with second level precision. And finally, the lambda function returns a datetime object, which is assigned to the datetime column of the data frame. And then I'm just executing that method, set datetime index on the original data frame. And so this is my datetime column right here, which is the index. And then the next step is the most important part of this exercise, which is feature engineering. So in this exercise, I will be doing mainly these 3 feature engineering before feeding the whole data frame to XGBoost for model prediction. And those feature engineering are the transform the timestamp into day, hour, minute, creating 3 new features. I will also build lag features, that is price at t-2, price at t-1, price at t, and price at t+1. And finally, create a window features of mean, max, and mean using the expanding method of pandas. So first thing first, which is the first feature engineering, transform the timestamp into day, hour, minute. And for this, I will be taking the last 3 years of data from the original data frame, because the original data frame has 24 million rows right from the beginning of 2015. But for this purpose here, for this XGBoost model prediction, I will be only taking the last 3 years. That is 2021, 20, and 2019. And so how many minutes are there? This many minutes in 3 years, because remember our data is again on a minute basis, and that's why I'm doing this little calculation. And I'm taking the last from the entire data frame of 24 million rows, I'm taking the last 15.7 million rows, representing the last 3 years of data. Alright, and you do that with just with the slice notation here. And I'm also not modifying the original data frame, and hence I'm creating a copy of the original data frame. And the new data frame is BTC shorter DF for training. And just after doing that, you just print the head It's just the same data frame, but only this time it is little smaller. And this is pretty easy actually, because this datetime is of the datetime format. We can extract the year, month, day, hour by just doing this kind of things. So first I'm creating a time column from my index datetime. And then from that time column, I'm doing .time.year, .time.month, .time.day, .time.hour. And I'm doing this for the entire range of the length of the BTC shorter DF for trading. So this will apply this particular format changes and new column creation for each of the rows. And then after doing this for year, month, day, hour, when I print the head, I have 4 new features. So these are those new ones, year, month, day, hour. That's pretty simple, right? And now the second feature engineering, which is lag features. And here the idea is to predict the value at the current timestamp based on the value from the previous timestamp. The number of previous time steps we use in our prediction is called the width of the time window or the lag. If we predict only one future time step, we are doing one step forecast. And we can also perform multi-step forecast and predict multiple next steps at once. This method is also called sliding window method with a window width of 1 in our case below. So here is our initial dataset. So we have timestamp T1, T2, T3 and the value for the corresponding timestamp as V1, V2, V3, which after this feature engineering will become value. So it will be shifted by one row. So here I have the initial is a undefined, because the initial value will become my Y, then X is becoming V1 and then V2. And that very much means that given the previous value V1, what is the target value? That is V2. Similarly, given the previous value V2, what is the target value, which is V3? So that's a whole fundamental basic concept here. So here note that the actual value for timestamp is gone from our data. We don't care about it anymore as long as we preserve the order. We only care about the actual value at the previous point in time. And we need to use a pandas dataframe.shift function here, which shifts the values vertically or horizontally and also fills in with nan values and leaves the index as it is. And for example, here I'm doing just that with only 2 or 3 lines of code. So first I'm just taking the close price with this line, and then I will need to concat 2 data frame. One is the original data frame, which is represented by TMP here, this variable. And the other new data frame is shifted data frame, which is tmp.shift. And I'm shifting by 1 row along the axis of 0. And so this line at temp.shift1 x is equal to 0 is used to create a new data frame that is shifted by 1 time step or 1 row along the time axis or x is equal to 0. This operation effectively moves each row's data 1 step forward, leaving a nan value in the very first row of the data frame. This new data frame has the same column names as the original temp data frame. And the whole concatenation of this along the axis 1 concatenates the shifted data frame from step 2 and the original temp data frame along the column axis, that is x is equal to 1. This operation results in a new data frame called lagdf with twice the number of columns as the original TMP data frame. Alright, so this was just an example for shifting the data frame, but for my actual implementation in this project, I want to create a data frame by shifting 3 rows. That is, I will have 3 data frames actually, one by shifting by 1 row, another by 2 row, another by 3 rows. And for that, I'm going to use a little util method create lagged data frame, which has been defined in the preprocess file. So here is that method. It takes a data frame and also a list of numbers as my lag values. So this lag value is just a list of lag values for shifting the data frame. And what I'm going to do is just using the list comprehension, looping through that and creating a single data frame for each of these lag values and then appending those individual data frame. So the important line here is just this, which is creating a list of shifted data frames. And then I am just appending to this list the original DF and finally concatenating all of the individual data frames. And so when I apply that method right here on my actual data frame here, I get this result. So we can see that this first one, I have 3 NaN values for the first 3 rows because it has been shifted by 3 rows. Then the next one, I have got 2 of them, and in the third one, I have got only 1. So, and finally, of course, this column represents the original close price in the original data frame. All right, with that, I come to our third feature engineering, which is window feature. So we already saw that how we can add a window of a certain width as a feature to be used by your model to forecast the value at a future time t+1. And beside using the raw values from the time window, that is a close price of t-1 or close price at t, etc., we can also compute summary statistics of these values and use them as feature for prediction. The most common aggregate value is the mean of the lag window or average of the lag window, and this is also known as moving average or rolling mean. So here is a quick representation of what is exactly happening under the moving average scenario. So the moving average can be used as a naive prediction model where the idea is to predict for the next day the average of the last W number of days, where W is the width of the moving average. So what you see right here, for example, I have the previous 2 closing price as V1 and V2. So the at T3, that is the next timestamp, my prediction would just be the average of V1 and V2. And that's the whole idea of using moving average. Now, while using moving average, one particular important thing to keep in mind is that while a moving average can be applied to both stationary and non-stationary time series data, but the insights derived from non-stationary data might be less reliable. It is therefore generally preferable to make the time series stationary before applying a moving average to ensure meaningful results. And the reason moving average requires stationary time series data is because the technique assumes that the statistical properties of the data are constant over time. If the data is not stationary, then the mean, variance, covariance, etc. of the data will change over time, and this will result in inaccurate trend prediction under the moving average technique. And here is a quick example of creating a Windows feature in a data frame, and just previously as we did, create a temp data frame by taking only the close column, that is, which has the closing prices of Bitcoin from the original data frame, and then create, then shift the data frame by 1 row, and that's what I'm using, temp.shift with a 1. And then create a rolling window with the next line, that is lagdf.rolling, and this line creates a rolling window object that contains a fixed size sliding window of data points which is centered around a specified point or a moving window that shifts over the data. The window function can be applied to a variety of statistical calculation, including moving average, rolling standard deviation, and even more complex function. And the window equal to 2 here just mentions that I'm taking previous two rows as my windows, and this is a shifting window or sliding window. And then in the next line, I'm just computing the mean of the rolling window and then concatenating this means data frame with the temp data frame. So, and the modified columns will be mean of 2 previous rows, and here 2 previous rows means t-1 and t, and the another row will be t+1, and then just concatenating it, and that's become my modified df. So the modified df will look like this, and you can see this column, the first 2 rows are NaN because we shifted by 2 rows here, and then And this is a mean because the first two rows doesn't have any mean to calculate over, because these two is the initial two rows. So that's why it has nan values. And this column has the actual value, which here represent the t+1. So yeah, so that's a very basic implementation. But what we are going to do now is using another pandas built-in method called expanding to create an expanding window, because our purpose here is this window size that we calculated here, this was fixed at 2, but our purpose here is not to have it fixed width. It can also be forever expanding window, and that's what we are going to do now. And about the expanding window, unlike a rolling window with a fixed size, an expanding window starts with a minimum size, in this case 1, and increases its size by 1 for each subsequent data point. So for the first data point, the window size is 1, as we can see here, and for the second data point, the window size is 2, and so on. The expanding window encompasses all previous data points, which results in the window size growing until it covers the entire data set. And then for each of the window size, you can calculate the mean, max, average, etc. And they will all be pandas series or pandas data frames with the same length as the original temp object. And finally, you concatenate the results of the mean, max, average calculation along with the original data shifted by -1. That is moving all values up by 1 position, and the concatenation is performed along the columns, what you see right here in this table. Now this is exactly what we are going to do now. So you start off with the original data frame, which in this case is tmp, and execute the expanding method on that data frame, and that's the result of that is a window. And this window data frame will have within it the mean, max, etc. So that's what we are doing here. So I'm concatenating all the window.mean, window.mean, window.max, and then window.shift by -1. That is lifting the data, lifting by 1 row, and defining the column names mean, max, t+1, and that's my data frame. And this is the form that it will take. And I want to point out this part again, temp.shift -1, because here we are shifting the entire data frame up by 1 row with shift -1. And why exactly we are doing that? Because this is done to align the target variable t+1, that is this one, with the current row's features, that is mean, and max, for predictive modeling. By shifting the data up, you are essentially trying to predict the next value in the sequence given the current row's expanding window statistics. And after this, this is our data frame, and that now I want to combine with our original, because as we know, we are all doing feature engineering, so we just got 3 more features here, and I want to add that to the original data frame. And so I am concatenating right here, pd.concat, then I concat the data frame which we just derived with the original BTC shorter DA for training. Now, and along the axis 1, that is along the column axis. So now this will become our final combined BTC shorter DA for training, and this is the data frame that we are going to use for our final XGBoost training. I just want to also show the how the data frame now looks like. So I'm just printing the head here of this combined data frame. And we can see that we have, in the original, we had open, high, low, close, volume, VWAP, and asset ID. Now we have mean, max, t+1, and also on this side we have year, month, day, hour. So many new features have been added. But still, this data frame needs to be cleaned up, because I don't want this asset ID column, for example, because that doesn't give any information, because all are 1. This 1 represent BTC price here. And also I want to take out this target variable, and that is a target column. And is there anything else I should take out? Okay, I think that's only 2. So what I'm going to do, I'm just going to clean up this data frame and create my X and Y for preparing the data to be fed into XGBoost. But first, for the XGBoost, I want to create a cutoff date, because from the same data set I want to cut off for train and test. So this is my cutoff date. Anything post this date is my test set, and any data before this date is my training set. And that's exactly what I'm just doing in these two lines. So I'm just making use of the index of my data frame. Anything with an index of below the target test cutoff date, that's my trend, and anything above, that's my test. So with that, I have a trend set of 5760, and okay, I think this is not the correct number. I may have just ignore this output. The correct output should be something like this. Trend.shape should give you 15 million or something rows, and test shape is 73,000 or so rows. And next, I'm just going to define all my feature names for the tabular data frame that I'm going to supply to XGBoost. And just like we discussed previously, I'm just deducting the target column and also the asset ID column, except that I am taking pretty much everything as my features. And the target value or the target column is, in this case, is a closing price of BTC. So that's the two things we have defined here. And then your X-train would be from the train data frame, you just take all the features, and Y-train, you just take the target column. So with that, your X-train and Y-train is ready. And just equally, you define your X-test and Y-test. So from the test data frame, you take only the features as your X-test, and your target for the test data set will just be from the test, you take XGBoost CD's target, right? Which is a closing price indeed. And then XGBoost training. So this is just a simple line of code here, but this method actually I'm defining in a separate file, train.py. So let's quickly take a look at that. Yeah, train XGB regressor. And it's pretty simple method. I'm just following the XGB package's official documentation to define all the configurations. And one thing to note is that use GPU to this method, this use GPU, this optional parameter I'm using by default false, but if you have GPU, you have to pass true when executing this method. Otherwise, all these regressor parameters is subject to change and subject to experimentation. So, and at the end, what it's doing is defining the XGB regressor and then applying fit method on that XGB regressor, passing your X-train, Y-train, and your eval set will be X-train, Y-train, X-test, Y-test. And we have already defined our X-train, Y-train, etc. like in 1 second before this. All right. And as to the definition of these various configuration for the XGB regressor, you can definitely check out their official documentation. For example, this base score, this is the initial prediction score for all instances, which is a global bias. The default value is 0.5, which is what I'm keeping it at. It doesn't have a significant impact on the model's performance, but it can affect the model's conversion speed. Then booster. So this is what this represents is a type of boosting model to use. Choices are GB tree, GB linear, or DART. The default is GB tree. And to note here is that tree-based models are usually more powerful but may be prone to overfitting, while linear models are simpler and might be suitable for certain problems. Then N estimators. This is the number of boosting rounds to run. Increasing the number of rounds can improve the model's performance, but it may also lead to overfitting. It is important to use early stopping rounds or cross-validation to find an appropriate value. And then early stopping rounds. Early stopping rounds is about the number of consecutive rounds without a decrease in the evaluation metric before training is stopped. This helps prevent overfitting by stopping the training process when the model's performance starts to degrade on the evaluation set. Objective is about the learning task and the corresponding learning objective. In this case, I'm selecting reg linear here, which means that we are solving a regression problem with a linear objective. Other options include binary logistic for binary classification and multi-softmax for multi-class classification. Max depth I'm providing 6. It's maximum depth of a tree. Increasing the depth can capture more complex patterns in the data but may lead to overfitting. It's important to find a good trade-off between model complexity and the risk of overfitting using cross-validation. All right, anyway, I'm not going through each one of them because you can just go through their documentation. Let's move ahead and run this. So when you run this, it may take anywhere between a couple of minutes to half an hour or so, depending on the power of your GPU. And after the XGBoost is finished running, the result is captured in this variable model. This is your trend model, and this contains much information. And the first thing I'm going to extract from this trend model is the feature importances. And for that, I'm going to use another little method, plot feature importance. And that method I am defining in trend.py. It's mainly using this particular thing, data, which is model.featureImportance underscore. So this is an attribute of the trend XGBoost model and contains feature importances as an array. These importances are computed as the average gain of the features when it is used in trees. The higher the importance value, the more important the feature is in making prediction. So in this method, I'm just creating a data frame called fit_importances with the actual numerical values of the feature importances and also the names of those features. And the names of the features I'm getting with this expression right here. So model.featureNamesIn is an attribute of the trained XGBoost model which contains the names of the features that were used for training. This is assigned to the index of the new data frame here, which means that each row in the data frame will correspond to a feature name. And that's it. And then I'm just doing a sort values on the importance and then plotting it. That's all. So when you plot it, you can see, like I was expecting, the top features are open, then low, high. Also, we have volume weighted average price as one of the important features, and also T+1. And these individual hour, day, month, year, they were almost non-existent in this particular exercise in terms of their importance to the XGBoost model. Alright, we are pretty much at the end, and the last and the most important thing of the entire exercise is to do the inferencing. And here we are at that step. So I'm just for inferencing, it's just a single line of code. You do model.predict and pass your test data set, and that will give you the predictions for your test data set. Alright. So after you get your predictions column filled in with the prediction values, that is, these are all the predicted Bitcoin closing prices for the range of dates within my test data set. Then you combine that with the original data frame. I'm actually merging it so that I can plot them together. And this is the final plot. So here the red portions are my prediction part. And actually these reds and the blue are overlapping. I'm plotting them overlapping each other because this is such a long period of length. We can, for this portion, we cannot almost see the blue part, but actually there is a blue part below this red part. So what actually it also means that the predictions almost are reflecting the actual values here. And I also need to point out that this was a baseline model. That is, all the feature engineering that I added was all pretty much straightforward, all the most commonly used for a time series project like this. So there is definitely many more scope for improving the feature engineering and improving the model itself. And in fact, in the very next video, I will do a LGBM model on the very same dataset and the same Kaggle competition, that is light GBM model. So stay tuned for that. Alright, that's a wrap for this video. Thank you very much for watching. See you in the next one.